So today we will study the étale fundamental group of schemes over a field of characteristic 0, not over complex numbers. So over complex numbers, we have this comparison result with the topological fundamental group. So the étale fundamental group is profinite combination of the topological one. But our goal is to get an idea what the étale fundamental group of schemes and characteristic P is. And so all the difficult computations go through kind of lifting to characteristic 0 and comparison with the topological fundamental group in characteristic 0. So we will develop some tools for doing this. Okay, so first I want to prove a very general result, saying that the fundamental group is invariant under infinitesimal thickening, of the base. So definition. So suppose I have a morphism of scheme. I will say that it is a universal homeomorphism if for any base change the base change map from x to y prime over y is a homeomorphism. Thank you. So two important examples. One is suppose you have a closet embedding you have a ring, some nilpotent ideal I, and say some power of this ideal is 0. So this is an example universal homeomorphism. So if you do a change, then it's still going to be closet embedding, and the ideal is still going to be nilpotent. So it definitely induces isomorphism on points, homeomorphism on points. Another example is the following. Suppose you have x over fp, any scheme in characteristic p over a field of characteristic p, then the Frobenius map, the absolute Frobenius map from x to x, which is defined to be the identity of and pth power on functions, is also an example of a universal homeomorphism. The second requires a proof. It's not. So if you do any base change, then it's no longer identity, of course, but it's a homeomorphism. It's not difficult. It's reduced. Okay, so now theorem is that if you have any universal homeomorphism, homeomorphism, then the base change map from finite et al. Covers y to finite et al. Covers of x, that say, let me, okay, x y prime over to the base change y prime times x over y is an equivalence of categories. And in fact, the same is true. Да. Yes. Над y, да. Над y. То есть у меня y штрих в y, x. Угу. Да, спасибо. Ага. Угу. So this is an equivalence categories, and the same is true, in fact, for an equivalence of categories we don't need here. So schemes et al. Over the change map equivalence category and the category of schemes over x. Okay. So and in particular, if you say then the same is true for x because it's a homeomorphism, then the map on pi 1 is an isomorphism. Okay? So let's prove this, and I will prove it on a special case of this to save time. So proof for infinitesimal thickening, so for closet embedding. So I will assume that f is of this type, as in the first example. So closet embedding with closet embedding with nilpotent ideal. Yes, but I will prove it in this case. In fact, right, yeah, I will prove in this case. So, нет, просто если у меня есть замкнутое вложение, и оно также является универсальным гомеоморфизмом, то тогда верно, что для каждого, что каждый элемент из идеала в какой-то степени равен нулю. Но вообще говоря, я не могу выбрать для всех элементов идеала одну степень, да? Да? Но в неутеровом случае...
Не утверждается, что любой там универсальный гомоморфизм.
Да, не утверждается. Вот есть пример. Вот этот фрагмент — это важный пример. Вот. Ну, в неутеровом случае, конечно, нильпотентности, локальная нильпотентность тоже. So, let's prove this. So, how are we going to prove that something is... Well, first, let's check that this base change functor is fully faithful. So, base change is fully faithful. Okay, so what do we have to show here? So I have some y, and I have y1, y2. These are, say, finite or just étale maps. And so I know that the restriction of these maps to X, I'm giving them a morphism. So we have y1 times X over y. We are given a map H to y2 to X over y. And we want, this is, to produce, to lift it. So we want to show that there exists a unique lifting. That's what it means that that this is a fully faithful on morphisms, right? Bijection on morphisms. So okay, so let's use the formal infinitesimal criteria of étaleness. So what do we have? We have y1, we have y2, we have a map from y2 to y. We have this map, and here I have y1 times x over y, and this is a closed embedding. Okay, now I have a map from this guy to y2 times x over y, which is a closed subscheme here. Therefore, I have this commutative diagram. So let's just look at this square here. So this is an étale map. And this is a closed embedding with nilpotent ideal. Right? So this is étale. And this is infinitesimal thickening. Right? And by definition of an étale morphism, there exists a unique map like this, which makes the diagram commutative. And this is our H tilde. Okay? Good. So this shows that it's fully faithful. And let's show that it's surjective on objects. So base change is surjective on objects. So, so it's since we already have notes, it's for any Italian. So, well, I'm proving really this assertion, which is more general than this one. So this is a local assertion. It suffices to prove now to construct. So I have an etalmorphism from some scheme X prime. So given an etalmorphism from X prime to X, we want to extend this to an etalmorphism from some Y prime to this larger scheme Y, right? So this is Y, and we want to produce some Y prime, which is an etalmorphism. Okay? So, well, I can do this locally. So, it suffices to do the following. For any point, say X prime in capital X prime, there exists a neighborhood open neighborhood, and open neighborhood, well, and etal map from W prime to Y, such that W prime restricted to X over Y is U prime. So once I have this, so I can, I know that already that, well, this this W prime is, if it exists, it's unique up to a canonical unique isomorphism, right? Which is compatible with this, right? Just by fully faithfulness. So we already know that there is only one way, unique extension of an etalmorphism from, well, of an etal cover of X to an etal cover of Y. So once I have this, I can glue this Y prime together and get an etalmorphism from, well, get a scheme Y prime together with an etalmorphism to Y, such that this diagram is commutative. So it's enough to prove the local assertion and then glue. So, well, and this is since this is a local statement, I may assume that all schemes involved are fine. So we are reduced to the following situation. So our X is spec A mod I. It embeds spec A, which is Y. I to the nth power is 0. And now we have a cover X prime, which is spec B, and B is of the following form. So B is the quotient of the polynomial algebra in some number of variables, modulo ideal generated by the same number of equations with the determinant of the Jacobian matrix dfi over dxj is invertible in B. So that's because any étale morphism locally looks like this by definition. So I have this B étale over this, and I want to extend it to an algebra étale over A. There is a natural, well, there's a kind of, let's just take let's take so I construct an étale map to Y, and let's take it. That's also going to be an affine scheme, where B prime is the quotient of the polynomial algebra, now with coefficients in A, equations Fi tilde with Fi tilde, where Fi tilde are lifts, arbitrary lifts of Fi. Okay? So now I think that the only thing I need to check is that this condition, the Jacobian criterion, is satisfied. But that's obvious because so if you compute the determinant of the Jacobian matrix, well, it will be an element of B prime. Its reduction modulo nilpotent ideal I is going to be invertible. So if you have an element which is invertible modulo, it itself is invertible. And this completes the proof. Okay? That's a very good question. And in fact, you can, so there is a okay. So, well, first of all, to answer your first question, so let's just take for the étale morphism an embedding of A1 minus 0 to A1. So we take a punctured line and embed it to a affine line. How can you write it in this form? Yes. So strictly speaking, well, even in this case of open embedding, it will not be of this form. However, it will be a localization, right? So if you consider, so B is a tal over A, and therefore any is a tal over localization of A. And if you allow yourself to have this freedom passing to localization, then it suffices to add just one variable. So, yeah. But I'm not, I will try not to use it until maybe later. Okay? So, okay, so then relatively easy result. And the next theorem, well, which is really a key result in theory of fundamental groups and even probably in total homology theory. So this is the following theorem. So let E be a complete local ring. So that means that I have A, I have maximal ideal, and A is equal to the inverse limit of its quotient, modular powers of this ideal. So a good example to think about is the ring of formal power series or the ring of periodic integers. Okay, and now let F be any proper then yeah, maybe I'll one notation. So let's denote by x0 the special fiber of this morphism. So it's going x 0 with A modulo maximal ideal. And I will denote the residue field by K. So, well, I have 0 is a subscheme of X. Well, at least it maps to X, and I have the base change factor. To X. Change, it goes to finding the tal maps to X0. The base change, and the claim is that this is an equivalence of categories. That's the assertion. So I will prove this. So we'll prove this in a second, at least in the Therian case. But before I give a proof, let's discuss what this theorem really means and why it's important. So corollary, let's say, if pi 1 of if x and x0 are connected, then pi of Italian fundamental group makes sense. Used map on pi 1 is an isomorphism. Okay? Well, remark. So what this really means is that, well, first of all, so here is a kind of informal remark. So imagine that you think of spectrum of A as a kind of small disk, formal maybe, small disk. Let's say we are working over complex numbers, and you have x. This is x, and this is x0. It's the fiber over the origin. So then, so the kind of the reason why this theorem is true is that, well, one should think that of x0 is kind of well, let's say a small neighborhood of x0 contracts to x0. That's kind of the picture you should have in mind. So, well, more precisely, so there is a similar assertion just in the category of well, for manifolds. If you have a manifold X, real manifold, together with a proper morphism to a disk, then there exists a tubular neighborhood, right? So if you allow yourself to shrink disk a little bit, then there exists a sort of tubular neighborhood of this fiber over the origin which is homotopy equivalent, which is deformation retract, such that x0, the special fiber, is deformation retract of the tubular neighborhood. So I am assuming that X is smooth. Well, yes. So in this topological setting, I don't know what a non-smooth manifold is, right?
But okay, for example, let's take E in a elliptic curve with constant reduction, some prime E. Please change E. How is it going to work?
So okay. So yeah. So I'm saying that if you have that's a very good example. So the picture could be more complicated as so this is you can imagine that you have a family, as you said, of elliptic curves over a disk, which degenerates into something like this.
So this is topologically S2 wedge SY.
S2.
If you have nodal reduction, if you have classical reduction, it's just
Okay. Well, so this is a family over a disk, right? So I claim that it's homotopy equivalent to this curve with node, which is just P. Yeah, but I'm not saying that the fundamental group of other fibers is the same. I am saying only that the fundamental group of the total space is the same as the fundamental group of the special fiber. Right?
But why can't you apply this theorem at any other point you want to ever see? You apply just at points.
Well, then you have to shrink. That's a very good question. But so if you choose another point, then sort of where the fiber is smooth, right? So my which does not intersect the singular fiber at all, right? Well, right. So indeed, if this morphism from X to the disk is smooth, right? In the sense of smooth manifolds, that the induced map, its differential is. Then, well, the result is easy. It just follows from. In fact, in this case, this map is topologically a fiber bundle, right? So if it's not smooth, then it's more complicated, and in fact, it's I really so I'm kind of so this is true in for complex analytic manifolds, but for real analytic manifolds, it's easy to give a contract. So if you just consider real curve, elliptic curve, degenerating into something like this, then it will be just false. So okay. So another remark is that the theorem is false without properness assumption. Okay, so let's construct a counterexample together. So let's even think of this first about this topological picture. So I have a smooth real manifold X with a smooth map. So I consider only smooth map for simplicity, and still it will be false. Small map, well, let's consider a map to a disk. And so I want an example where this tubular neighborhood is not whose fundamental group is not the same as the fundamental group of the special fiber.
Well, first projection, A minus 0 to A1.
So here you can do very simple things. So maybe I will. I think it's equivalent to what you suggested. So if you do not impose this properness assumption, you can do you can take a proper family. Let's say constant family of P1s, right? And now just remove finite number of points. from the special fiber, right? So you take P1 times open disk, and then you remove finitely many points from the fiber at 0. And then I claim that the complement, the fundamental group of the complement, will not be the same as the fundamental group of the P1 minus finitely number of points. Well, indeed. So you this kind of this whole family, this total space, is a disk. So now move finitely many points. When you have something smooth of dimension 4 and you remove finitely many points, it doesn't, because when you remove of something of codimension greater than 2, right? It doesn't change the fundamental group. So, but of course, if you look only at the special fiber here, you remove something of, well, you take P1 minus finitely many points, it has a large fundamental group. So it's still true that you have a kind of, even in this non-proper case, you still have a neighborhood of the special fiber which contracts to the special fiber. But this neighborhood is no longer tubular in a sense that it doesn't contain a cylinder like this, right? So it will be, I will draw a picture here. It can be something like this. So you have like as point and x0 goes to infinity, this neighborhood becomes thinner and thinner. So it doesn't, you can restrict yourself to a smaller disk. So that if you can construct a tubular neighborhood, that's what happens in differential geometry. So let's produce a sort of, again. Ну, давай вспомним, как допустим, что у тебя есть вот дифференциальная геометрия, гладкое многообразие x и гладкое подмногообразие x0. Значит, всегда есть такое общее утверждение, что существует окрестность открытая окрестность x0, которая стягивается на x0. Как это делается? Используется метрика. Строится на x римового метрика, а потом с помощью римового метрика мне задает экспоненциальное отображение. Если вектор, я могу провести единственную точку на многообразии касательный вектор, провести единственную геодезическую, значит, через эту точку с заданным касательным вектором. И с помощью этого отображения можно построить такое x0, вот такую окрестность. Значит, как это делается? Вот, значит, я беру какую-то вот точку здесь, и я провожу, значит, во-первых, у меня вот есть все касательное пространство к x, оно канонически распадается в сумму двух: горизонтального и вертикального. Точнее, вертикальное, как бы оно инвариантно определено, это вертикальные касательные вектора, а горизонтальное — это просто ортогональное дополнение. Если у меня есть метрика, то я могу такое сделать. Теперь значит, как я хочу строить стягивание маленькой окрестности на x0? Я беру какую-то точку и провожу через нее геодезическую, заданным касательным вектором, скажем, длины 1, горизонтально. Ну, то есть, вот что это означает горизонтальным вектором? Вот у меня есть на диске моем есть векторное поле, стандартное векторное поле, там, я не знаю, которое z, d по dz. И я это векторное поле, я могу поднять его вот сюда. А потом через эти точки проводить геодезически, и вот будет такое стягивание определено. Но вообще говоря, геодезически их не всегда можно продолжать до бесконечности. То есть может такое случиться, что что вот вы начнете с какой-то точки, проводите геодезическую, а эта геодезическая никогда не пересечет специальный слой. Такое запросто бывает. То есть, или лучше, наверное, это сказать иначе. Вот для каждой точки у меня есть такое экспоненциальное отображение вот у меня есть x и x0. И есть экспоненциальное отображение, это отображение из некоторой окрестности нулевого сечения в нормальном рассвоении в x. Это отображение, оно индуцирует гомеоморфизм, даже дифеоморфизм, между некоторой открытой окрестностью нулевого сечения в нормальном рассвоении и открытой окрестностью x0 в x. Открытая окрестность, она не обязательно содержит прообраз какого-то маленького диска. Вот в этом все дело. Хорошо? Да, здесь я предположил гладким. Кать, понятно, что происходит. Да. Ага. Вот. Okay. So let's produce an example. So let's take just for x p1 say times c bracket c minus 2 points, say okay, so what I mean here is that this scheme has a closed subscheme, which is just P1, right? It corresponds to the special fiber, T equals 0. And here I have this, just 2 points. So my x is obtained from this constant family by removing 2 points from the special fiber. So it will be like this. And now I remove 2 points. This is 0, and this is infinity. And now I claim that so this P1 minus 2 points, this scheme has a finite cover, right? This is the multiplicative group. So x0 is the multiplicative group GM. And it has a finite cover, which is, say, GM, and the map x goes to x squared. And I claim that you cannot extend it to a finite total cover of this scheme X. So assume that you can, right? So you have so you have X, you have X0. So here I produced for you this this map x0 prime, and so you can construct some x prime, which is also finite total, such that this is a Cartesian square. What we will have? So this x inside, so I didn't change the generic fiber, so it has one tensor C double bracket T. And I can restrict my finite total cover. So let's say x prime C double bracket C, right? So I have a finite total cover of P1, and it definitely has a, well, I'm not saying that any cover of P1 over this guy splits, but the fundamental group of this guy is just the Galois group of this field. So which means that if my cover has this, if this guy has a C bracket T section, point, sorry. So well, let me first make a claim. This splits. Okay? Is it clear what splits? So I have P1 over some non-algebraically closed field. And I have a finite étale cover. A few lectures ago, we proved that the fundamental group of P1 over an algebraically closed field is 0. That is a more general assertion. If you have P1 over any field and a finite étale cover together with a point with value in this field, then it has a section. Right? So that means that this guy is not connected, but this is an étale map, so that means that this is also not connected. A section. A section. Yes, so, well, what we do is the following. We take any map from spec C to this guy, and then using the étaleness of this map, we extend it to a map from spec C T to this guy. Right? So why can I do this? Just by induction. I construct a compatible system of maps from spec. I apply the infinitesimal criteria of étaleness to map from spec of polynomials modulo power of t and construct the lifting of this section. This gives me this point, and therefore it gives me a point here. Good. So this theorem is important. So let's see, this one. So how we are going to use it? The theorem. Well, so let's take spec A and let it be the generic point. Say, let's A be a domain. Generic point. Okay. Now, so then what we can do, we can consider pi1, the map from the fundamental group of the generic fiber of X, right? So we have X over spec A, we have X0. This is the special fiber. I recall that small k is the residue field. So A mod M is k. And let's say that fraction field of A is capital K. It's the residue field of this generic point. So I have X eta sitting here. And right, so this is spec K. So I have a map from this to pi 1 et al. Of x just by functoriality. That's used by Wadim, which by the theorem is isomorphic to the fundamental group of x0. Okay. Now let's take another map from this time from the spectrum of algebraic closure of this generic point, and let's call the fiber the pullback x eta bar. So this is a geometric point, right? And composing this map is this one, the map from pi 1 et al. Of x eta bar to this group. So we construct this homomorphism, which is called the specialization map on the fundamental groups. So again, in topology, what we would do, we would take let me draw this picture here. So we have our disk. We have here x0. So here we have this is the generic fiber, which is x eta. And what is their kind of picture for x eta bar? So x eta bar is obtained from x eta by tensoring, by taking the fiber product with universal cover of the punctured disk. So we take this this whole family, we remove x0, and we take the kind of the fiber product with the universal cover of the punctured disk, which is upper half plane, if you wish. It's the exponential map. So so again, for smooth manifolds, this guy here is homotopy equivalent just to fiber of this family over a point close to 0 but not equal to 0. Generic fiber. Geometric generic fiber. So we get a map from fundamental group of the generic fiber to the special fiber. Okay, so you could phrase it in topology. You could just do it directly. So take this closed fiber, say over. So this is 0. Take some point A, which is not equal to 0. This fiber, it embeds into the whole family, and the whole family is homotopy equivalent to the special fiber. So you get a map from the fundamental group of this of the fiber over A to the fundamental group of fiber over 0. That's the specialization map. So here we do not make any smoothness assumption at all. So we always have this map, provided that the family is proper. So the next step in study of fundamental group will be to show that under smoothness assumption, this map is always an isomorphism in characteristic 0. And in characteristic P, we will show that it's surjective, and it's an isomorphism on prime to P, prime to characteristic quotients, finite quotients. So if you have a quotient by an open normal subgroup, which has order prime to characteristic of the residue field, then these quotients are sort of in one-to-one correspondence here and here. Okay? Which means that any covers of x0 and of this guy, which are Galois covers of order prime to characteristic P, so they are projection. Very good point. Very good. Yes. So for the second assertion, right? I need to assume this. Thank you. Thank you. So maybe I will write it. So I want to keep this. So it's kind of the preview. Next theorem is that the map from pi 1, if the fibers of spec A of X to spec A are geometrically connected, then the induced map, the specialization map from pi 1 et al. Of x eta bar to pi 1 et al. Of x 0 k is surjective. And isomorphism on prime to characteristic k quotients. Right? Okay, so this is really powerful theorem. For example, if you have a curve of, suppose you want to compute the fundamental group of a smooth proper curve over a field of p elements, or over, better to say, over algebraic closure of a finite field. So what would be the strategy? So you can, first of all, it is known and easy that any curve over a finite field can be lifted, smooth curve over a finite field can be lifted to a smooth proper curve over ZP, over periodic integers. That follows from vanishing of the second homology group of Uran-Schiff. So, no, just over ZP. Oh yeah, so over ZP.
No, if you say over FP bar.
So start with a curve over FP. And then you can lift it to a curve over ZP. And then you can use the theorem to compute, so the special fiber x0 will be your original curve over fp. So this will be a curve over fp bar. And so we get a surjection to this fundamental group from a group that we already know, because this is a scheme over, this is a curve over 2p bar, right? And we know that its fundamental group is the same as the profinite completion of the topological fundamental group of a curve of genus G. So we get a surjection from a known group to this group, and moreover, this surjection has a controllable kernel. So it's an isomorphism primed to peak quotients. Okay.
Можно еще раз повторить? Исоморфизм на чем?
На конечных факторах по открытым подгруппам, у которых порядок взаимопрост P с характеристикой поля вычетов.
Does this mean that the kernel is just a from P group?
No, because it's not. No, because let's see. This pro-P group is not. No, it doesn't mean that. So suppose you have a homomorphism of. I know that G prime. And I'm saying that it's an isomorphism on this map induces an isomorphism on prime to P quotients. What does it mean? It means that if you have a surjection G mod H is normal, then there exists a normal subgroup here, G prime H prime, and an isomorphism like this. That's what it means. So for any normal subgroup, open normal subgroup, say quotient as prime to be stronger normality.
And the inclusion of A5 into the monster group is an isomorphism of prime to 5 quotients.
Yes, yes. Okay, very good. So let's prove this theorem. And I will prove it only in, well, if you want to really prove it from scratch, this is a deep theorem. And if you want to prove it from scratch, it will take a year-long course. It's so Grothendieck developed some machinery exactly for doing things like this. In particular, he developed theory of formal schemes, and that's what I'm going to use here. Okay. Proof. I will prove it under extra assumption that A is Noetherian. And A. Okay. So what you do, you look at schemes xn, which is x times spec of A modulo maximal ideal, and plus first. So you have x0, and you have a family of infinitesimal chain of infinitesimal thickness. Okay. So so I will just so this chain of infinitesimal thickness define what's called a formal scheme. So it's a line topological space with x0, but the ring of functions on this script x is the inverse limit of functions on xn. So now the proof is based on the following. The proof of this theorem is based on the following algebraization theorem. Правильно, спасибо. Okay, so here is the statement. Suppose you have this map is proper, and suppose we have a diagram x0, x1, x2, and suppose we are given some finite maps, compatible system of finite maps, h0, h1, from some so hi are finite, and so this they are compatible in the sense that if you all these diagrams are Cartesian squares. So zi times x I over xi minus 1 is zi minus 1.
What are assumptions on the tau? What do we need from zi for it to?
I'm not going to well, not so in order to define formal schemes, all you need is that this maps are closed embeddings with nidpotent ideals. Okay, but I'm not. So this kind of tower of this sequence of finite maps should be thought of as a finite map to this script x, to this formal scheme. But I defined explicitly what it means, right? Да. Then, no, after all, yes, but I do not make any a priori assumptions on that. Да, то есть из того, что квадраты Декартова следуют, ну, что-то, да, мы сейчас увидим. В общем, нет, апостериори они будут ограничены. Then there exists a finite étale map. There exists a scheme and a finite étale map to x such that Zn is obtained from Z by base change.
Nowhere we said that HI are etal.
Yeah, I do not make this assumption at all. Mm-hmm.
This is rather suspicious because what if we take Z? Wait, so what is H a finite etal or is it just finite?
Just finite.
Oh, yeah.
So let me give you here an example showing why this theorem is non-trivial. Oh, maybe, let's see. So I have, I don't want to give this example now. I will give it next time. I want to finish the proof. The proof will be very, okay. Of the theorem, so of this theorem, okay, so the key part here is the essential surjectivity of this functor. In fact, well, this is really the kind of the hardest part, and the rest can be proved using the same technique, as I'll explain now. But it's easier. So let's focus on the essential surjectivity. So, well, I have x0, and I have some x0 prime, which is finite etal. And I want to predict a finite etal cover of x. So what can I do? First, I take x1, and this is an infinitesimal thickening by our topological invariance of the fundamental group. There exists a unique cover, finite etal, such that, so this is finite etal, So as we already learned, so this extends to also finite etal cover, uniquely extends to finite etal cover of x1. And then you can extend it to a finite etal cover of x2, and so on. Да. И здесь никакой собственности не нужно. Мы так... Да, спасибо. So you construct these maps, then apply algebraization. Get a finite map from x prime to x, and I claim, so its restriction to x0 is this, and I claim that this h is finite etal over x. So what is that? So what do I have to prove? I know that it's finite. All I need to show is that it's etal. So I need to show that it's flat and that the sheaf of relative Euler differentials is 0. So let's check that it's flat. So what does it mean that it's flat? It means that the direct image of the structure sheaf, so rho star of x prime is a vector bundle. Okay, you know that it's a coherent sheaf, X, and you know that it's that modulo the ideal, maximal ideal, it's a vector bundle. Because of generality, you may assume this vector bundle is trivial. So just take a collection of sections that trivialize this vector bundle, leave them arbitrary to sections of this guy, and this will be a trivialization. Right? So why it's a null? So you need to show that the Keller differential, the sheaf of Keller differentials, is 0. So let's take the sheaf of Keller differentials of x prime over x. This is a coherent sheaf on x prime. Look at its support. Support is a closed subset of x prime. This map is proper, the support must intersect the special fiber. Right? This map is proper. So if you have any coherent sheaf here, its support, well, any closed subset of x prime must intersect the fiber, the over x0, right? The closed fiber. So, but the original, this map is étale. So its intersection of the Keller differentials with the special fiber is the support of the Keller differential with the special fiber is trivial. So that means that it's étale. Okay, I think I need to stop here. So next time I will make some more comments on this algebraization theorem. It's the reference for this is Hartshorne book, No Algebraic Geometry, and it's called the Theorem on Formal Functions. But I will explain how it follows. Да. Да. Ну да, конечно, потому что что такое степень ошитого? Это ранги вот этих векторных рассвоений. То есть у меня просто... Что? Ну, она автоматически ограничена. Даже вот просто если без всякой собственности. Если у меня есть такая диаграмма, то отсюда следует, что значит, у меня есть прямые образы ошитых.
Но если z, например, если z приводимое, то...
z0, тогда z0 приводимо, да. Они же, это же не... Нет, ну как, у меня же есть вот это вот условие, значит, топологически все эти пространства, они просто одинаковые. Вот эти все вложения, они индуцируют изоморфизм на топологических пространствах. Как я могу что-то добавить?
Нет, ну в смысле это просто компоненты, как бы, в которые задать. Ну представь, что у тебя флаг вложений такой есть, а сверху ты можешь добавлять просто компоненты, которые проецируются в x, но z не лежит в них. Ну как бы компоненты.
Нет, но это же все-таки, вот это все вложение с нильпотентным идеалом. Да нет, да даже до алгебраизации. Но вот это вложение с нильпотентным идеалом. Поэтому, в частности, они индуцируют, вот все эти вот топологические пространства, они одинаковы. Здесь они тоже одинаковы, поэтому ничего я не могу добавлять. То есть, конечно, значит, в нашем случае вот это будут рассвоения, и они все одинакового ранга. Потому что если я это рассвоение ограничу на меньшее x и t, то получится просто, почему они все одинакового ранга? Ну, просто потому что если я ограничу вот это рассвоение с x этого на x минус 1, то получится, ну, соответствующее, вот, значит, если я его вот эту штуку ограничу на x минус 1, то получу h и минус 1 со звездочкой от o z и минус 1. Это вот условие. Поэтому, значит, апостериори, конечно, ранги у них у всех одинаковые. Не подскакивать не могут. Вот. Хорошо. Есть еще вопросы?
Сейчас, то есть ты все-таки хочешь сказать, что верхние строчки это тоже утолщение нипотента?
Ну, конечно, да, потому что...
Вот это я не понял.
Да, это следует из этого условия. Как же не следует?
Ну, копии x, x2, например, да.
Хорошо, но если я добавлю z2, например, x2, то тогда, когда я сделаю замену базы, у меня из этой компоненты получится x0 лишнее. Хорошо. Есть ли еще вопросы? Но если нет, то...